Hello everybody, welcome back to the Ultimate Physics channel. The topic of this video is Ehrenfest Paradox and its resolution. In the year 1909, 4 years after Einstein had published his Special Theory of Relativity, Paul Ehrenfest came up with the paradoxical situation when applying Einstein's special theory to the problem of a rigid rotating disk. Let us see what the paradox is. For a rigid rotating disk of radius r, when it is at rest, its circumference is 2 pi r. When this disk is set into a rotational motion with an angular speed that is constant, whose value is omega, then special theory of relativity tells us that in directions parallel to the direction of motion, the object would undergo Lorentz length contraction. That means, since the disk is rotating along the periphery of the disk, the elements of its circumference have to undergo length contraction, whereas the radius, which is the perpendicular direction to the direction of the motion, there would be no contraction. If that happens, one can clearly see that, let us call the circumference C. When the disk is at rest, the ratio of the circumference to the diameter is equal to pi. 2 pi r over 2r. D is 2r. The diameter of the disk is 2r, right? Now, during rotation, according to special theory of relativity, the elements of the periphery of the disk has to contract due to Lorentz length contraction, and therefore the circumference should be less than the circumference that it has when it is at rest. And therefore let us call that circumference when it is rotating as C prime, and the C prime must be now less than 2 pi r prime. Since radius is not changing, r prime is equal to r, that means d prime is equal to d, and therefore the ratio of C prime to d or d prime is now less than pi. We know that the ratio of the circumference to the diameter of a circle is always pi. Ehrenfest found that this is a paradoxical situation, that for the same disk, when it is at rest, its circumference to diameter ratio is pi, and when it is rotating, this ratio is less than pi. He found out that this is a paradoxical situation and it has to be resolved, and he argued that there is either a problem in our understanding of the geometry, or that could be a problem with the special theory of relativity or its applicability to the problem of rigid rotating disk. Now let us discuss the historical context within which Ehrenfest proposed this paradox. In the year 1909, the same year when Ehrenfest proposed this paradox, Max Born had earlier suggested something called bond rigidity, in which he tried to find out what kind of objects are equivalents of rigid bodies in classical mechanics. So he wanted to study how rigid bodies would behave in special theory of relativity. So he had proposed a set of conditions and constraints for objects to behave as rigid bodies within the purview of special theory of relativity, but his paper discussed objects that are linearly accelerated and those objects that move along straight lines. This was Born's original paper. Now, Ehrenfest wanted to adapt bond rigidity conditions to the problem of rotating objects. When he tried to apply this to problem of rotating objects, he found out that it is impossible to take objects from a state of rest to a state of uniform rotational motion with a constant angular speed omega without deformation. So he argued that either our understanding of geometry is wrong, or there could be issues with the special theory of relativity. In fact, Paul Ehrenfest was not an advocate of the special theory of relativity originally. So he wanted to find some issue with the theory, and he of course found an issue in the form of this paradox. So he wanted an explanation for this paradox or resolution of the paradox. His original paper was a very simple note. In fact, he had applied the original idea to the problem of a rotating cylinder rather than a disk. But later on, people realized that the third dimension here in this case, which is the height of the cylinder, hardly matters in the resolution of this problem. Whether it is a cylinder or a disk, it does not matter much. There is a paradox and it needs resolution. Let us now get into the resolution of this paradox with a simple argument, and then we can further dive into the details later. When this paradox was presented to Albert Einstein, he was already working on the development of the general theory of relativity. So Einstein's simple resolution of this paradox was like this. An observer in the rotating frame of reference, which is the frame of reference of this rotating disk, would find that the geometry of this disk is non-Euclidean. And therefore, any measurements that he makes in this frame of reference would not be agreeable to an inertial observer who would make a measurement of the ratio of the circumference to the diameter as being equal to pi. So the observer in this frame of reference, which is a rotating frame of reference, did not agree with this observation of an inertial observer. An observer in this frame of reference would be deemed a non-inertial observer because a rotating frame of reference is an accelerating frame of reference. And therefore, in such frames, observers would probably not agree with the measurements made by inertial observers, and therefore, in fact, Einstein simply, in his communications and in his personal communication to some of his peers, had simply resolved this by saying that the geometry of this disk appears to be non-Euclidean, and therefore the value of the ratio would be greater than pi. In fact, he did not agree with the Ehrenfest agreement that it should be less than pi. Einstein had proposed that this ratio must be greater than pi. In order to understand how this paradox is resolved and how this ratio is greater than pi, we need to go into the details of the geometry of the problem. For over 2000 years till the 19th century, we were aware of only one kind of geometry that follows Euclid's axioms and postulates, and that is called as the Euclidean geometry. The basic ideas of the Euclidean geometry are taught to us at an early stage of our education, and many of these ideas appear trivial to us. Some of these postulates include: Euclid's first postulate is about the shortest distance between any 2 points on a plane, and it is a straight line. Euclid's second postulate is about the extension of this straight line, that is, any straight line can be extended to infinity. Euclid's third postulate is about the circle. Given a center and a constant distance, one can draw a circle which is the locus of all points at a constant distance from a center. Euclid's fourth postulate is about the constancy of the right angles, that the angle between any two objects at right angles is always 90 degrees. It is Euclid's fifth postulate that created a lot of upheaval in mathematics for over 2 millennia. This fifth postulate is also called as parallel postulate, and it can be expressed in several ways. One of the ways in which, when expressed, this postulate is very simple and easy to understand is attributed to John Playfair in the 18th century. This postulate goes like this. Given a point and a straight line, the point being not on the straight line, one can draw only one straight line passing through this point and parallel to the first line. Mathematicians tried to prove this postulate for over 2 millennia, but in vain. One cannot prove this postulate. One cannot prove Euclid's fifth postulate from first principles. But in trying to prove Euclid's fifth postulate, mathematicians realized that there could be non-Euclidean geometries. Some of the non-Euclidean geometries include elliptical geometry, more specifically spherical geometry, and hyperbolic geometry. One of the derivations of this fifth postulate is what is called as the postulate of triangle. The sum of the angles of any triangle is equal to 180 degrees. Even the Pythagoras theorem is a derivative of this postulate. Mathematicians realized from the fifth postulate that this is not always true. There could be non-Euclidean geometries where the sum of the angles of a triangle need not be equal to 180 degrees. They in fact found out that in the case of the elliptical geometry, this angle is greater than 180 degrees, and in the hyperbolic geometry, this angle is less than 180 degrees. And similarly, the ratio of the circumference to diameter of a circle is less than pi in elliptical geometry, and it is greater than pi in hyperbolic geometry. It is with these ideas in mind that Einstein proposed that the geometry of the rotating disk is non-Euclidean and it could be hyperbolic. Coming back to the problem of the rotating disk, Ehrenfest had realized that it is impossible to accelerate a rigid object from a state of rest to a state of constant angular speed. In fact, if such an acceleration is carried out, there would be deformation. Ehrenfest had predicted that at high velocities, if an object is accelerated this way, it would shatter into pieces. There is also a question of the applicability of special theory of relativity to rigid objects. In fact, special theory does not allow for the existence of perfectly rigid objects. In fact, the speed of sound in such perfectly rigid objects would be equal to speed of light, which is not permitted by special theory of relativity. We can also use a thought experiment to prove that this is true. Suppose we have a rod of length slightly greater than, let us say, 1 light year. If this object is a perfectly rigid object, if a push is given to this rod or it is tapped at one end, this would be transmitted instantaneously to the other end, and the other end of the rod would move at the same instant. This would violate the second postulate of special theory of relativity, that nothing can travel faster than the speed of light in vacuum. The information that this rod has moved has traveled faster than the speed of light in this case, and therefore that would violate the fundamental postulate of special theory of relativity, and therefore perfectly rigid bodies are not possible according to special theory of relativity. So the rigid rotating disk in this case need not be perfectly rigid. It is not a perfectly rigid object by any means, but and it cannot be accelerated from a state of rest to the constant angular speed of omega, but a rotating disk as such can be studied using special theory of relativity. In fact, a disk that is in a state of rest, if it is accelerated to a state of constant angular speed omega, it would violate Born rigidity. Once it is rotating at a constant angular speed omega, then one can apply special theory of relativity. It is in fact in this context that the problem of rigid rotating disk is discussed here. In fact, it is shown that if a disk is rotated from a state of rest to a state of constant angular speed, even for smaller speeds, it can be shown that the shape of this disk deforms into something like a cup. Now that some of these fundamental ideas about the geometry of the problem as well as the physical limitations of a rigid object have been discussed, let us move into the resolution of this paradox. Let us assume that the disk is now rotating at a constant angular speed, and let us place an observer at the center of this disk. As the radial distance from the center increases, at different points the velocity keeps increasing, because we know that for a circular motion the linear velocity is a product of the radial distance and the angular speed. V is equal to r omega. Therefore, at different points on this disk, the linear velocity keeps increasing, but at the center V is equal to 0. So, at the center of the disk, when r is equal to 0, V is equal to 0. And at the periphery, where we see the maximum effects of length contraction, or where we would expect to see the maximum effects of length contraction, r is equal to capital R and V is maximum. So this problem, when we discuss the velocities, it is generally attributed to the maximum velocity at the periphery of the disk, and therefore if at all there is length contraction in this problem, that would be maximum at the periphery of the disk. So if we place an observer here, he might see some effects of length contraction in a direction parallel to the direction of motion, that is along the periphery of the disk or along the circumference of the disk, but he would see that there is no contraction of length along the radial direction, because that is perpendicular to the direction of motion. So the radius is not shrinking, but the circumference is shrinking. That is what he should feel, or he would see, this observer. But in science, we don't go by what we see. The notion of seeing is believing is not always true in science. So we go by what we can measure, what we can observe and what we can measure. That is more important. Let us say we hear two sounds simultaneously. We might assume that these two events that caused these two sounds must have occurred at the same time. But if we go and investigate, we might find that these two sounds originated at different locations and they traveled different distances to reach our ears, and we felt that they were simultaneous, but they were in fact not actually simultaneous, or they were not result of simultaneous events. The same way, in this problem, what this observer at the center sees is immaterial. What he can measure is important, and Einstein has suggested ways to make measurements in special theory of relativity. The two important instruments of measurements in special theory of relativity are clocks and meter sticks. So, if some kind of measuring rods or meter sticks are placed around the circumference or periphery of this disk, then one would see some contraction of these measuring rods or sticks. So from an inertial observer's point of view, for example, this observer whose velocity is 0 at the center here, he would probably be able to see some kind of contraction of the measuring rods placed along the periphery, but how could he confirm anything on this? That could be due to the elongation of the periphery as well. or that could be due to the contraction. So exact measurements he is not in a position to make. The same is the case for an observer who is hovering over the top of this disk, let us say. He would be able to more clearly see the contraction of the measuring rods, but he wouldn't be in a position to make any measurements himself. He would probably even assume that the gaps that are forming between these rods, these measuring rods which are kept originally close to each other, there would be gaps because of contraction. These rods are length contracting now, Lorentz length contraction occurs, and there will be gaps. And he might conclude that he would need more number of such rods to fill up the gaps, and therefore the number of rods that you would require now to measure the same circumference is more, indicating that the circumference has elongated. So he might even agree with Einstein in that case. Now Albert Einstein resolved this paradox this way. He wanted an observer to be on the periphery of this disk with a meter stick that is not going to contract, or a measuring rod that is not contracting, and if he goes around this disk trying to measure its circumference, he would in fact find that the circumference has elongated. Now this is a heuristic argument provided by Einstein without any solid mathematical proofs originally. Such arguments only we call heuristic arguments, because Einstein probably intuitively felt that because of the geometry of the problem, he might have felt that an observer going around the periphery might find that it is elongated rather than contracted. So he might not even agree with Paul Ehrenfest's original proposal that there would be length contraction along the periphery. Einstein predicted that there would be an elongation of the circumference of the disk. The circumference in fact elongates for the observer who is traveling on this disk. Understand a lot of important issues regarding such an object. A rotating disk has different velocities at different points. So any clocks carried by observers, different observers on this disk, would have different time dilations. And those clocks, if you try to synchronize with any clock carried by inertial observers, it is impossible to synchronize these two clocks, at least according to the Einstein clock synchronization criteria. Einstein also told that it is impossible to agree upon simultaneity of events for the observers on this frame of reference. So one cannot assign a frame of reference to this rotating object. Now, according to bond rigidity, there are two ways in which such a rotating object can be accelerated. If this disk is considered to be made up of a large number of tiny elements of some length, and if some kind of uniform acceleration is provided to each of the two ends of all these elements, then it is possible to accelerate all these elements simultaneously, and the disk starts rotating because of that acceleration. Or it is not starting to rotate, rather it is actually accelerating further, because from rest you cannot accelerate a disk of this kind. So you have to further accelerate from a constant velocity omega, let's say, to another velocity omega plus d omega. That is possible. If that is done in this way, it is found mathematically that this would deform the disk. It would probably even shatter into pieces if that is done. So that way of accelerating this, according to bond rigidity, is not possible. There is another way in which this can be accelerated, that is by providing a uniform acceleration of this disk according to an observer who is inertial or at rest with respect to this disk. That is, an observer who is not rotating with this disk, if an acceleration is provided according to him, then this can be accelerated. If such an acceleration is provided, where the disk is uniformly accelerated according to an inertial observer, the elements of this disk would not feel a uniform acceleration. The elements of this disk would feel not a simultaneous acceleration. That is, two ends of this disk, for each element of the disk, each element out of which the disk is made, these two ends would see a time delay between the accelerations. Let us call the time delay between. I'm not going into the mathematical rigor of this problem. It is not within the scope of this video. I'm just trying to explain the problem in its details. So each element, the two ends of this element will see a time difference between the acceleration. In fact, the front end would accelerate, let us say, earlier compared to the farther end, which would accelerate later. And this difference in acceleration would be seen as an elongation or a distance, corresponding distance, by an observer walking along the periphery of this disk. So as an observer walks along this periphery of the disk, this is the reason why he would see a corresponding distance measurement, because of this time difference in acceleration. And that is how this problem is resolved. So the conclusion of this problem is that the observer walking around the periphery would find that the geometry is non-Euclidean, and he would find that the circumference in fact is longer than when the disk was at rest. That brings us to the resolution of this problem, but this problem has been keeping scientists busy for over 100 years now. Even now people are debating a lot of things about this rotating disk problem. What is it that keeps scientists busy on this problem? What are the issues connecting this regarding this problem that keeps scientists busy? A lot of things. First of all, to begin with, one cannot accelerate a disk from rest to a constant angular speed, and of course no perfectly rigid disks are possible within relativity. But does the speeds which this disk can withstand, does it depend on the material of the disk? If that depends on the material of the disk, what kind of materials will withstand what kind of speeds? This is regarding the material aspect of this problem. There are other questions also. This rotating disk problem has always been seen as a problem that straddles the boundary between special and general theory of relativity. And therefore, if the disk is made up of a real material and it is massive enough and it's rotating also, you can see that the space-time around this disk would be curved. So one has to study the space-time curvature around such disks. In fact, the importance of Ehrenfest paradox in the development of general theory of relativity cannot be overemphasized. In his communications, Einstein had consistently referred to this problem during the time he developed the general theory of relativity. Ehrenfest paradox seems to have inspired Einstein into using his own principle of equivalence and the non-Euclidean geometry and incorporated that as the nature of the geometry due to gravity, and thereby he ended up successfully developing the general theory of relativity based on these things. So there is some kind of inspiration that Einstein got from Ehrenfest paradox, which is obvious, but he did not communicate anything on this problem, I think till about 1916, when he started finalizing his general theory of relativity. He had communicated in some personal letters and notes about this problem of rotating disk, but he did not formally publish anything on this till a very later stage. Now, regarding the principle of equivalence and its connection to the general theory of relativity in the context of the Ehrenfest paradox is uh, that the rotating disk is an accelerating frame of reference. An accelerated frame of reference is a non-inertial frame of reference, but according to the principle of equivalence, one can assume that an accelerated frame of reference which is non-inertial is equivalent to an inertial frame of reference in the gravitational field. For example, for an observer on this disk, he can claim that his disk is not accelerating or rotating, but it is in a gravitational field. And any observer who is inertial observer with respect to disk is free falling. So that forms the essence of what is called as the principle of equivalence. Knowing the principle of equivalence beforehand and linking this problem to that principle of equivalence and equating this non-Euclidean nature of geometry in this problem, he was able to link it up to the presence of non-Euclidean geometries or curved space-times in the presence of gravitational fields, thereby ending up developing his general theory of relativity. So that confirms that Einstein was right about the resolution of this paradox. The geometry of this problem of a rotating disk is in fact non-Euclidean. That brings us to the conclusion of this video. Hope it answered some of the questions that you yourself had on the Ehrenfest paradox. Thanks for watching. If you enjoyed this deep dive into the Ehrenfest paradox, please like, subscribe, and hit the bell icon to get notifications on more such mind-bending physics content on this channel. Leave a comment below with your thoughts and questions, and let me know what topics you'd like to see next. Cheers.